Welcome to a refresher lesson for trigonometric functions, properties, and operations. This is part one of two parts in this, excuse me, in this section of properties and operations. And in this part, we will focus on right triangles and unit circles. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So when we talk about trigonometric ratios, we always start with right triangle trigonometry. And the ratios are ratios of the sides of a right triangle with respect to one of the acute angles. So you can see in our right triangle here, we have the angle labeled T. And so with respect to that angle, we have a leg or side that is opposite that angle. We have a leg or side that is adjacent to that angle. And then we have the longest side of the right triangle opposite the right angle, which is our hypotenuse. And so the sine of that angle T is simply the ratio of the opposite side over the hypotenuse. The cosine of that angle T is the adjacent side over the hypotenuse. And then the tangent of that angle T is the opposite side over the adjacent side. So sine, cosine, and tangent are just shorthand to let us know which ratio of sides we're talking about. So if you are asked to find the sine, cosine, and tangent in a right triangle, that's what you're looking for. And you may remember that there is a mnemonic that will help you to remember which sides for which trig functions. The mnemonic is SO, CA, TOA. SOH stands for sine, being opposite over hypotenuse. CAH is cosine, is adjacent over hypotenuse. And TOA is tangent, being the opposite over the adjacent. So in this case, we're using the Greek letter alpha as the way to denote which angle we are talking about. It's very common in mathematics that unknown angle measures are denoted by a Greek letter, but it's no different than having an X or T or anything else. It's just a symbol that represents an unknown. And in order to find these ratios, we don't need to know what the angle actually is. We just need to know the sides so we can set up the ratios. So for the sine of alpha, sine is opposite over hypotenuse. The opposite side is the 8. The hypotenuse is the 17. And so the sine of alpha is equal to 8 over 17. If we want the cosine of alpha, then we want the adjacent. So the adjacent side is the one that is connected with that angle. So that's the 15 over the hypotenuse again, which is our 17. And so that's going to be 15 over 17. And then if we're looking for the tangent of alpha, we want the opposite over the adjacent. So we'll go the opposite again with 8 over the adjacent again, which is the 15. And so the tangent of alpha is 8 over 15. Now, many times we are given right triangles where we don't know all of the sides. So you may have to find one of the sides first before you can set up the ratios. As in this case, we know that side A is 20. We know that side B is 30, but we don't know side C, the hypotenuse. But we also know that because this is a right triangle, Pythagorean theorem applies. So I have an A squared, which will be 20 squared. I have B squared, which will be 30 squared, and that will help me to find C squared. So 20 squared is 400. 30 squared is 900. 400 plus 900 will be 1,300. And then I'll take the square root of both sides. Now, because we're dealing with a triangle, we're not interested in the negative result of the square root. So we're only looking at the square root that is positive of this 1,300. And if we want to do a little bit of simplifying, we can see that 100 is going to be a factor of 1,300. And 100 is a perfect square, so we can simplify this to a 10 root 13, excuse me. So this now is our hypotenuse. So now when we go to find the sine of angle B in this case, so this is the angle we're interested in, our opposite side is the 30. And our hypotenuse is the 10 root 13. Now, if you were a student in my class, I would expect that you simplify the 30 and the 10. I do not necessarily expect you to rationalize. Now, you need to check with your own teacher as to what their expectations are, but I would not necessarily ask you to rationalize this. So 3 over root 13 would be fine if you were my student. If we go to our cosine, the cosine of B, so our adjacent side now is the 20 over the hypotenuse of 10 root 13. Again, we could simplify the 20 and the 10 to make it 2 over root 13. And then for the tangent, we would be taking the opposite side of 30 over the adjacent side of 20, and we can simplify that to 3 over 2. All right, now with right triangles, we have a couple of right triangles that are called the special right triangles. And it's good to know the relationship of the sides in these special right triangles, because this is going to help us with where we're going with our unit circle. So if you notice here, the first right triangle is what we call the 45, 45, 90 right triangle, or an isosceles right triangle. Because if these two sides are equivalent, then that means those two angles are equivalent, then we know those two sides have to be equivalent, which means we have an isosceles. The relationship of the sides in an isosceles right triangle is that obviously these two legs will be equivalent, and then the hypotenuse is always going to be that value A times square root of 2. Okay, always happens. That relationship is always there when you are dealing with a 45, 45, 90 right triangle. Similarly, in a 30, 60, 90 right triangle, we need to know which angle is the 30 and which angle is the 60, and obviously which angle is the right angle. Now, the side, the leg across from the 30 is always kind of our starting place. So that's going to be our A value. And then the side or leg that is across from 60 is always going to be that A times the square root of 3. And the hypotenuse is always going to be 2 times A, twice as long. Okay, so we can use that to find missing lengths a little bit more easily if you can remember these relationships. For example, in this 45, 45, 90 right triangle, we know that the legs are going to be our A values. Okay, so the 4 is our A. And we know that the hypotenuse is always going to equal the square root of 2 times that A. So if we know that a leg is 4, then we know the hypotenuse is going to have to be the square root of 2 times 4, or 4 root 2. Similarly, in a 30, 60, 90 triangle, we can see that this is our 30 degrees if this one is our 60 degrees. And so if we're starting here, we know that x has to equal the A value. We know that 60 across from that has to be square root of 3 times that A. So this 12 has to equal the square root of 3 times A. And then we've got our hypotenuse, which will have to be 2 times A. So using the side that we know, we can solve this equation. We can divide both sides by square root of 3. And then here I probably would want to do a little bit of simplifying and rationalizing just to see what we get. So I would end up with a 12 root 3 over 3. And then our 12 and 3 can simplify, and I would end up with a 4 root 3, which is going to be a little bit nicer to work with than 12 over root 3. So if that is what A is equal now, then we can go to our x side, and we know that x will have to equal that A of 4 root 3. And then we can go to our y side, and y will have to equal 2 times our 4 root 3, which will be an 8 root 3. Okay. All right, so this is usually where we start, is with our right triangle trigonometry. But then from that, we want to expand into being able to do the trig ratios for any angle. So in a right triangle, we are limited to just acute angles. We want to be able to expand that to talk about any angle. And so we're talking about any angle. We're now shifting our thinking from triangles to rotation. And so we are rotating ourselves, our angles around a coordinate plane, so to speak. And so when you have a problem like this that asks you to find sine, cosine, and tangent for the angle and standard position if the terminal side passes through the point -4, 3. Well, a standard position angle means that, excuse me, we start here at the positive x-axis, and then we're going to rotate clockwise if it's a positive angle. So I'm sorry, counterclockwise if it's a positive angle, or clockwise if it's a negative angle. Okay. Now here we don't know information about the angle. What we know is that the terminal side, so where the other ray for this angle is going to stop, goes through the point -4, 3. So it's going to go through this point right here. So that means that this angle has rotated in this direction. We're going to assume the smaller distance. And our terminal side now is going to go through this point. Okay. Very common Greek letter to represent angles is theta, which is kind of an O with a big loop in it. And so this is the angle that we're interested in. And again, we don't have to know what that angle is if we can figure out something about the sides of things, right? So if this is the angle, what we want to do is we want to create a right triangle because we know how to do the trig of right triangles. And we're going to do that from this point by dropping down a perpendicular line to the x-axis. You always make your perpendicular line from the point to the x-axis. Okay? And then that creates, with the x-axis, a right triangle. And so now we can apply our right triangle knowledge. Okay? Inside of this triangle, this angle right here is what we call a reference angle. And so a reference angle is often denoted by a little prime mark after it. So if I'm calling this original angle my theta, then my reference angle is going to be theta prime. And the interesting thing about trigonometry is that for whatever angle I'm interested in, the trig for the reference angle is equivalent to the trig for the original angle. Okay, so if I find out the trig ratios inside of this right triangle I just created using this reference angle, those will be the answers for my original theta. All right, so how do I find my distances? Well, from my point, this was the point -4, 3. That means I know I went -4 units here, and then I went 3 units up. So I already have 2 of the sides in my right triangle. And using Pythagorean theorem, I can come up with my hypotenuse, the distance from the origin out to that point, which is going to be 5. Now having the measurements for all 3 sides of my right triangle, I can write my trig ratios. Now, I'm not going to write theta prime here because theta is what I'm originally looking for. And as I just said, whatever trig values work for theta prime work for theta. So I'm going to say the sine of theta is equal to my opposite now over the hypotenuse. So that's going to be a +3 over 5. My cosine of theta, we don't normally label sides of triangles as being negative, but in this case, we're going to keep that negative as part of the answer because we need to know the direction that we went as well as how far, and that affects what our trig ratio is going to be. So we are going to use -4 as the adjacent side over 5. And then for the tangent of our angle, our opposite, whoops, sorry about that, there we go. Our opposite over adjacent will be 3 over -4. Okay, so you can see now that depending on where we end up in the circle, depending on where our terminal side is and the point that it goes through, we can have some trig ratios be positive and some be negative. And so it does make a difference what direction we're going, and we want to make sure we include that when we set up the ratios. So in general, if you have a point that you know the terminal side passes through, you can use that to set up your trig ratios. So R in this case represents that distance from the origin to the point, which becomes our hypotenuse. And we're always going to find R by taking the square root of x squared plus y squared. Okay, because basically The X is always one leg, the Y is always the other leg, and this is a version of the Pythagorean theorem. And so if that's the case, then the sine will always be the Y coordinate, over R. The cosine will always be the X coordinate over R. And then our tangent is always going to be the Y over the X from that point. We don't need R for tangent. Okay. Now, because of the possibility of getting positive and negative results, it is sometimes good to think through, what is that going to look like? What should I expect for my results, depending on which quadrant my terminal side is going to be in? So if you remember with quadrants, we count from our upper right quadrant first, and then we go counterclockwise. Okay. And so in quadrant 1, we know that we have positive X values and positive Y values. In quadrant 2, our X's are negative, our Y's are still positive. In quadrant 3, both X and Y will be negative. And in quadrant 4, our X is back to being positive, but our Y is still negative. So if that is the case, then that means the sine of an angle with a terminal side in quadrant 1 will always be positive because our Y is positive. The sine of an angle with a terminal side in quadrant 2 is also going to be positive because our Y is positive. The sine of an angle in quadrant 3 will be negative because now Y is negative. And the sine of an angle in quadrant 4, it will be negative because, again, Y is negative. We're looking at cosines. If the angle's terminal side is in quadrant 1, our cosine will again be positive because now X values are positive. If the terminal side is in quadrant 2, then our cosine will be negative because now the X value is a negative. Same in quadrant 3, cosine will be negative. And in quadrant 4, our cosine goes back to being positive because of that X coordinate being positive. And then finally for tangent, if tangent relies on both X and Y, having a positive Y over a positive X will give us a positive result. In the second quadrant, having a positive Y over a negative X will give us a negative result. In the third quadrant, a negative Y over a negative X actually gives us a positive result. And in the fourth quadrant, a negative Y over a positive X will give us a negative result. Okay, so it's good to be familiar with what you should expect from whether it should be positive or negative based on the quadrant that that terminal side is in. And if you want a quick mnemonic that will help you to remember that, you can use the mnemonic all students take calculus. Not that they have to, but that's the saying that you can use. And use the first letter. So all means everything is positive. Okay, all three are positive. Students tells you that in quadrant 2, only the sign is positive. In quadrant 3, take tells you only the tangent is positive. And in quadrant 4, the calculus tells you only the cosine is positive. So that's a way that you can remember what sign to expect in which quadrant. All right, now taking that information, that knowledge, we want to apply that to what we call the unit circle. And in a unit circle, we specifically are saying our R, our radius, is going to be 1. So our hypotenuse is always going to be 1 in the unit circle. In the unit circle, we have a circle with a radius of 1, but we still have those XY axes through the middle of it. Okay, so we're still talking about points that make up the circle being one distance away, 1 unit away from the origin. And we're still talking about the points on that circle being XY coordinate points. Okay, so if we take what we talked about, before here with our general ratios for sine, cosine, and tangent, we are now taking the R and replacing it with a 1. So now the sine of an angle is going to be y over 1, which is just the y coordinate. The cosine of an angle will be x over 1, which is just the x coordinate. And the tangent is not affected. It is still y over x. Okay. The other thing we need to realize is as we are moving into how trig works in a unit circle, we generally start moving into using radians instead of degrees. So degrees and radians are both ways of measuring angles, just like we have inches and we have centimeters to measure lengths. Degrees are mostly used when you're working within a triangle. Radians are usually more commonly used when you're working within a unit circle. And you can always convert back and forth. You can take a radian measure times 180 over pi and get the degree measure. Or you can take the degree measure and take it times pi over 180 to get the radian measure. But we are going to, for the rest of this lesson, be working mostly with radians. Okay, so when you're talking about this unit circle, again, you see we have the circle itself. We have X and Y axes through the circle. And you can see there are points on the circle at different intervals around. Okay. If we take those special triangles that we talked about a moment ago and set them on the circle, we can come up with what's called the special angles on the unit circle. So for example, if I take the triangle with pi over 4, which is 45 degrees, and I set that on the positive first quadrant of my unit circle, you can see here I have one acute angle that's at the origin. And then I have the right triangle here set up with this point. And so using this right triangle, I kind of want to figure out what are the coordinates for that point. Well, we know that the hypotenuse is 1. That's the radius of our circle. That's what a unit circle is. So we know that. And we know the relationship is that each leg will be an A, and the hypotenuse will be root 2 times that A. So with a little bit of algebra, go root 2 times a, we can discover that a must be equal to 1 over root 2, which if you rationalize becomes root 2 over 2. So both this side and this side become root 2 over 2, which means then that my distance from the origin out horizontally was root 2 over 2 units, and my distance up to the point was also root 2 over 2. And so that would be my coordinates for that point. You can also see then from that if I was looking for the sine of 45 degrees, I would be taking the opposite side over 1. And so I would get root 2 over 2 as my answer. Same with the cosine of 45 degrees. The adjacent side would be this root 2 over 2 over the 1 for my hypotenuse. So root 2 over 2 would also be the value for cosine of 45. And if I wanted to find the tangent of 45, I would be taking the root 2 over 2 that's the opposite over the root 2 over 2 that is the adjacent, and I would just get 1. Okay, now if I take that 45, 45, 90 isosceles right triangle and I place it in the other quadrants, what I'm getting, let me erase this for a minute so it's not too messy here. Okay, so we said we've established that this is a, which is root 2 over 2. This is also a equal to root 2 over 2, while this is 1. Okay. Now, those distances don't change. What changes is the direction I went to get there. So if I'm looking for the coordinates for this point, now I'm going the same root 2 over 2, but in the negative direction. And then I would still go up to get to my point. And so that's still going to be a positive root 2 over 2. This is still going to be a radius of 1. But this is now, even though this is my reference angle, which is 45, the actual angle going from our initial side and rotating to this as my terminal side, this is actually the angle 3 pi over 4, or 135 degrees. Okay. And then if I continue rotating, I would rotate down to here, which would be an angle of 5 pi over 4, which would equal 225 degrees. And if I continued over to this side, then we would be looking at 7 pi over 4, which is equal to 315 degrees. Okay, so I technically am looking at different angles depending on which quadrant we're in, but the reference angle for the right triangle that gets made is always that pi over 4. So my sides are always going to be root 2 over 2, and root 2 over 2. It's just a matter of, am I going left, right for the x coordinate? Am I going up or down for the y coordinate to get the positive or the negative? Okay. Similar thing happens with pi over 6, which is 30 degrees. We know from our special triangle that opposite of 30 degrees is where a is. This is going to be root 3 times a, and this is going to be 2a. Well, again, we already know this value is 1 because it's our radius. So again, a little bit of algebra tells us that a, sorry, not sure why my iPad is being weird about that. There we go. Try again. There we go. Okay. So if I'm taking, man, sorry. Haven't had this issue before, so let's see if we can fix it. So if I'm taking the fact that 2a equals 1, then that means a has to equal 1/2. So that tells me that side. And then this side means I would be taking the root 3 times the 1/2 to get root 3 over 2. So now if I'm looking for the sine of pi over 6, or 30 degrees, that would be the 1/2 divided by 1 for my hypotenuse. The cosine of pi over 6 would be the root 3 over 2 over 1. And then our tangent for pi over 6 would be the 1/2 divided by root 3 over 2. If I change that into 1/2 times 2 over root 3, I end up with 1 over root 3. And if we rationalize it, we would call that root 3 over 3. Okay, and again, all of these angles in the different quadrants are technically different angles, but they all have the same reference angle. So this would actually be 150 degrees, or 5 pi over 6, but it still has that 30 degree or pi over 6 reference angle. And so our sides are going to be the same no matter where we go. It's just a matter of this now becomes negative root 3 over 2, and this is a positive 1/2. This was positive root 3 over 2, positive 1/2. Down here, our point would be a negative root 3 over 2 and a negative 1/2. Here, we would have positive root 3 over 2 and negative 1/2. And so you can see again how this x coordinate represents our cosine and this y coordinate represents our sine. Because in each case, that side is being taken over 1, and so it's just that value. Finally, we can do the same thing with our pi over 3, or 60 degrees. And so the same concept applies with our, with our 30, 60, 90. Now let me use green this time so it's a little bit easier to see. We know that if this is the 60, this must be the 30. So that makes this A. We know this then across from 60 is going to be the root 3 times A, and this becomes the 2A. Well, again, that's just equal to 1. So A is still going to be 1/2. It's just now along the x-axis. And this is still going to be root 3 over 2. It's just now on the vertical. So this point now is going to be 1/2 root 3 over 2. If we go over to this angle, which would be a 2 pi over 3 or 120-degree angle, having that same reference angle of pi over 3 or 60 degrees means that this is now a negative 1/2, and this is still positive root 3 over 2. If we go to the third quadrant, this point is going to be negative 1/2 and negative root 3 over 2. And then for this point, we would be looking at positive 1/2 and negative root 3 over 2. And again, this represents the cosine of that angle. This represents the sine of that angle. So if we put all of that together, this is what you get. These are the special angles of a unit circle. You can see it in both degrees and in radians. You can see the coordinates for the point on the circle for each of these angles. And in each of those coordinates, we know that the x coordinate will be cosine, and the y coordinate will be sine. And then if you want tangent, you simply take y over x to get those. One last point, you'll notice that there are some additional points in here. If you are at 0 degrees, 90 degrees or pi over 2 radians, 180 degrees or pi, and 270 degrees or 3 pi over 2 radians, then we don't need the right triangle to figure out the point because we actually are straight on the axes, and we can tell that we are 1 unit out and 0 units up or down. Or we can tell that we are 0 units to the left or right, but we went 1 unit up. Or we went 1 unit to the left, 0 units up or down. We went 0 units left or right, but 1 unit down. Okay, so these 16 special angles are ones that you need to commit to memory if you have not done so already. These are going to be used in just about everything you do with trigonometry. So make sure that you are committing these to memory as much as you can. Okay. All right, so very quickly, if you want to find the trig value then, the sine of 4 pi over 3, for example, you would find 4 pi over 3, which is right here. To take the sine, you would go with the y coordinate, and that is a negative root 3 over 2. If you want the cosine of 11 pi over 6, 11 pi over 6 is there. We take the x coordinate for cosine, and we get a positive root 3 over 2. We want the tangent of 3 pi over 4. 3 pi over 4 is right there. We're going to take the y over the x. Okay, so we're going to need to use both of these, the y over x. Since that is a positive root 2 over 2 divided by a negative root 2 over 2, we are going to get a negative 1. All right, I know that was a lot, but hopefully if you are still a little shaky on trigonometry, I hope that you have found that helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.